What does this look like to you? An op-amp. How could you tell the difference between an op-amp and a comparator? From its schematic symbol. Pardon? Part number. Yes, if it's labeled, the part number is the way to do it. Right now, do you know the difference if I said if I labeled this LM339? That's a comparator. Oh, okay. Someone with a bit of experience. As you gain experience, you'll get to that point where you can look at the number and say, oh, I recognize that. That's a comparator. And before we're done today, I'll show you some other things that you can look for in the circuit so you can that will give you a hint as to whether or not you're looking at a comparator or an op-amp. So, characteristic-wise, it has the same description, honestly, as an op-amp. High differential gain between the inverting and the non-inverting inputs produces an output. Same rules about the output. If the non-inverting input is at a higher potential than the inverting, it's going to drive the output up. If the inverting input is at the higher potential, it's going to drive the output down. The fundamental difference between an op-amp and a comparator is in their intended operation, and therefore the optimizations that people have made internal to the device. An op-amp is intended to be an amplifier, a linear device. You put in a little bit of voltage, you get out a proportional larger voltage. A comparator is designed to make a decision. Is this input above or below? Is one of my inputs above or below the other? And so if it's above, it's going to drive the output all the way up. None of this, if it's a millivolt above, I'm not going to get, a gain of 1,000, so 1,000 millivolts on the output. I'm going to drive it all the way to the op-amp, or all the way to the rail. Technically, if it's a microvolt above, I'm going to drive it all the way to the rail. So internally, this device has been optimized for switching, and in particular focus on switching speed. The result is they've made all sorts of optimizations that lead to a nonlinear response inside the device. So while you can make a passable, just passable, but you can make a passable comparator out of an op-amp, the converse is not true. You cannot make an even passable amplifier out of a comparator. Internally, it will not operate in the linear region the way you would like it to. It's going to be highly nonlinear in its operation. So, in a pinch, you can turn an amplifier into a comparator, although it will be slow. But you can't do flip it around the other way. You can't use a comparator as an amplifier. All right. There is another difference that's not specific to comparators, but it applies to the vast majority of comparators. On the order of, I think I did some numbers, I might even be I mentioned it in the book, something on the order of 80%, if I'm remembering correctly, of comparators have a different style of output than an op-amp does. Op-amps have this style of op-amp output, which is called push-pull. And it's push-pull because you can both source current, that's the push part, and you can sink current, that's the pull part. Okay? All op-amps have a push-pull kind of output. It can't produce the sort of linear amplifier without being able to both push and pull on the output voltage. Comparators often, most often in fact, they leave out this sourcing transistor. And so they create a configuration that in bipolar terms is known as an open collector output. And it's called an open collector because if you look at the output pin, it's just tied to the collector of that lower transistor. So what's going to be the implication of that in terms of what I can do with the output voltage? Pardon? I can't. Can I source? No, you're supposed to be answering questions, not. No, you shouldn't be scared of giving the wrong answer. The worst I'll do is say, eh. So it doesn't hurt. So what's your answer?
Can't source.
Can't source. But that's not the answer to my question. But that's okay too, because I just get to ask the question again. What can I do with the output voltage with this? I can only drive it low, which is related to can't source. And what it means is I can only pull the output low, so I can only sink current, because sinking current is how we make an output go low. Sourcing current is how we make the output go high. So with an open collector output, you can't source, the device itself cannot force the output to go high. So how are we going to get the output to go high then? Or do we just, is this one that's either low or it's not there? Yes, a pull-up. If we add an external resistor to the output, then this external resistor can cause the output to go up. And that adds a level of flexibility because the plus that I use on the other side of the resistor doesn't have to be the same plus as the power supply for the comparator. So I can take a comparator with 5-volt supplies, pull this up to, for example, 3.3 volts, and make up an output that goes from 0 to 3.3 volts if I want to connect to a device that likes to see 3.3 as its input. Depending on the comparator, even if it's powered at 5, I might be able to hook this output resistor up to 5 or to 7 volts or 12 volts, depending on the particular comparator spec. When we get into looking at real comparators later in the quarter, I'll show you where to pull out of the data sheet what the maximum pull-up resistor value or pull-up voltage is that you can use. So this is called an open collector when it's made with a bipolar junction transistor with a BJT. If it was made with a MOSFET, what terminal would be open? The drain. And so when MOSFETs are used, we call this an open drain output. Functionally, they have the same characteristics. That is, you can't source current, you can only sink current, you can only make the output go low. Something external has to make the output go high. Slight differences in leakage current and low voltage that they can achieve, but the basic behavior is the same. Okay, so let's take a look at our first comparator circuit. So start getting used to it. LM339, actually a 139, a 239, or a 339. Those are all comparators. They all behave they all behave in more or less the same way. There's tighter quality control on the 1s than on the 2s than on the 3s. And we'll get into the non-ideals. So if you see something that's a 139, 239, or 339, should jump out. Okay, comparator. Here's the other thing that's going to be a hint that you've got a comparator. This one is a hint because it's not always present, just in the vast majority, is if you see a pull-up on the output. It's rare that you will see a pull-up on the output of an op-amp. It's very common to see it on a comparator. So if you see a pull-up on the output of this op-amp-like symbol, that's a good hint that whatever's there is likely a comparator. And if you don't recognize the number, go hop on the web and look it up and check to be sure that is indeed a comparator. So we can apply an input voltage to the non-inverting input. Just completely arbitrary which one I did. And then I use a voltage divider to set a reference voltage on the other pin of the comparator. And if Vin is, so we'll call that Vref. If Vin is greater than Vref, what do I expect the output voltage to be? Pardon? 5 volts. Why 5 volts? Because that's what I've tied the pull-up resistor to, and because the comparator is seeing that the voltage applied to its non-inverting input is larger. And so it's going to drive the output, or it's going to do what it can to drive the output up. But with an open collector output, all it can do to make the output go up is turn off that output transistor. So it turns off the output transistor, and we depend on our pull-up to make the output go up to 5 volts. And conversely, it's a binary system, so if Vin is less than Vref, we'll get something that's approximately 0 volts. Yes? How would you figure out that you need a pull-up resistor for some arbitrary comparator? Well, see, that's the point. I guess the answer to your question is you're going to look at the data sheet. Once we get to data sheets, it'll be really clear. It'll say open collector output, or they're not always as clear as we would like them to be. But I'll show you the things to look for in the data sheet so that even if they're not clear, you can deduce that this device has an open collector output. There are some things that if they are present, you know for sure it's got a totem pole output or a push-pull output on it. And there are other specs that if they're present, you can deduce that it's got an open collector output. Yes? Do the golden rules of op amps apply to comparators? That's a good question. Anybody? You say no? Yes? What?
Well, one of the golden rules of op amps is that the two inputs of positive and negative are equal, right?
Right.
I mean, if that were true here, it would be.
Okay. So that brings up that because excellent point. We have a golden rule that says the inputs are at the same potential. There's a requirement on that golden rule that you seem to have forgotten. Well, actually, the bit about the terminals having a very high gain is not one of the golden rules that I gave you. Okay? It's one of the requirements that leads to a golden rule. It leads to the golden rule that those two inputs are going to be at the same potential. But there's a requirement that was forgotten there. Yes, it's only true that the two inputs are at the same potential if it is in negative feedback. And it has infinite gain. That combination is what drives those two voltages to be exactly the same. So what about the input current? What's different about if I just look at the input side? Would I expect anything to be any different? No. And so some of the golden rules apply and some don't. All right? The golden rule about no input current, that's a good one. That applies to both op amps and comparators. But we are not going to operate comparators in negative feedback, so we can't apply the golden rule about the inputs being at the same potential because that requires that we be operating the device in negative feedback. So from a circuit analysis standpoint, no current in or out of the inputs, that's good. We're going to keep with that. Yes. Really? Where's the negative feedback? Oh, this is really good. This is really good. Because I'll agree, it does kind of look like negative feedback, but it's not. I've tied this point here to 5 volts, so it's not going to move. So I don't care what I do on the output, it's not going to affect what this voltage is over here. Yes?
So in this case, can we go through it like we do with an op amp and say that no current is going to the input, so you can say V in, but if V in and Vref are different and there's no resistor in between them, then there's no voltage drop, that's really drop between two terminals.
Which 2 terminals? So we can do it the same. We can apply the same sort of golden rule about the input current. So we can say there's no current flowing there. That's 0. So what that means is this is just an ideal voltage divider. And we apply the voltage divider equation to figure out what Vref is. And now we compare Vref with Vin. And that allows us to predict what the output voltage is going to be. Yes, Kyle. No, if Vin is larger than Vref, the device is going to try and drive the output high. But because it's got an open collector output, all it can do is turn off that sinking transistor. All it can do is turn this device off, which it's going to do. That's what it does in response. If Vin is greater, if the input at the non-inverting input is greater, then it's going to turn off the open collector output transistor. And then the pull-up resistor is going to pull this point up to something that approximates 5 volts. And how close it gets is going to be determined by how much current is being drawn by whatever we hang off here over at V out. And if Vin is less than Vref, we're going to turn this transistor on, and it's going to pull this point down close to ground. That's why I said approximately 0 volts when I wrote that down. It gets down for a bipolar output device down to between 100 and 200 millivolts, depending on how much current. For a CMOS device, it can get even closer, within a few millivolts of ground. Yes, Indu. Hypothetically, if Vref is equal to Vin, what happens? Could it ever be exactly equal? No. So that's the answer to your question. There's an infinite gain being applied to 0 input, then it would be 0 output. But it's a situation that physically cannot exist. And so we can do mind experiments, but they're not very useful in terms of building circuits. Yes? Okay, that's a very good question, because I spent many hours one afternoon trying to figure this out. Long time ago. What's going to happen if I don't have the pull-up resistor? But I don't have. I pull it out. When I say don't have, I'm pulling it out. I'm not shorting it. Okay? Pull it out of the circuit. What's going to happen to V out? Will I leak current until V out rises? Where would I be leaking current from? So I'm going to leak it from the base to the collector. But the base is only at 0.6 of a volt because the emitter is tied at ground. And if you use the diode model, which is maybe what you're thinking about, there's another 0.6 of a volt, so there's no potential to drive that up. So I'll save you, yes. Wouldn't it just have problems sourcing current? Well, you have to source even at least a little bit of current to measure a voltage, because we don't have any perfect measurement instruments, so it's going to have to source a little bit of current. But there's no way, there's no path for it to source current. And so what you're going to get is, what's the ambient noise that's being coupled into your voltage probe? Sometimes it reads high, sometimes it reads low. What I found was that when the device was activated, bang, it'd snap right down to 0 volts and read a nice clean 0. And then when it was supposed to turn off, it would meander around, and then it would turn back on and snap down to 0. But without that pull-up resistor, there's not going to be any consistent voltage that appears on that pin. And you're going to pull your hair out trying to figure out, why is this not going where it belongs? Okay? So, pull-up resistor, absolutely required if you want to actually have a high voltage on that output. So what